In this presentation, we talk about some of the properties of light. So we'd like to be able to talk about how we actually see objects, and in order to see objects, we need light. So that light can come from many different sources: sunlight, lamplight, anything like a fire that's glowing. But in general, we need to have light to see objects because the light reflects off of objects, and those reflections of light reach our eyes, and that's how we see. We can't see clearly in a dark room because we don't have enough light to reflect off of those objects. And in fact, if it's completely dark, like if you've ever gone on a tour of a cave, they will shut off all the lights and you can actually put your hand right in front of your face and you can't see it. So we need light to be able to see objects. So the way that we see objects is that we model light as rays of light. And those rays represent a very small beam of the light that is actually present. So there's lots of rays that are present, and we just look at small sort of like bundles of rays. And light travels in straight lines, so it doesn't bend around different things, but it can reflect off surfaces and then travel in a different direction. So in this particular picture, we have a pencil, and we're looking at a particular point on the pencil right here. And this pencil is in a room that is lit, and so there's lots of rays of light that actually hit the pencil, and then they reflect off of the pencil. And they reflect off of the pencil in all possible different directions. And then there's an eye over here. So a small bundle of those rays of light that reflect off of the pencil surface actually hit the eye. The eye and the brain interprets those rays of light as coming from some point on the pencil, and that's how we see the eyes, or that's how we see the pencil and see the object. So if we follow those rays of light back, they seem to originate from a point on the pencil, and that's how our brain interprets that there's an object present. So it turns out that the law of reflection is still valid, just like it was for all waves, including sound waves. And the law of reflection basically says that when a ray of light is incident on a surface, it reflects off at the same angle that it was incident. So one of the important things when you're measuring the angle of incidence and the angle of reflection is you have to draw a line that is perpendicular to the surface at the point of contact. That's called the normal to the surface. And then we measure those angles relative to that normal. So here's a picture of a laser pointer hitting a surface, and the angle of incidence is equal to the angle of reflection, and there's that normal line that's drawn in there. So let's talk specifically about a plane mirror. And when we're talking about a plane mirror, it's a flat mirror, right? So a straight mirror. And we could talk about how images are formed. So for any given object, so here is the object over here, we have an infinite number of rays of light that leave the object that after it's reflected off, and they're going to hit the surface of the mirror. And then the law of reflection says they're going to reflect off at the same angle they're incident, so they diverge from one another. And the eye is over here somewhere, and the eye believes those rays of light traveled in a straight line, and so if you follow all of those rays of light that diverge back, that's what the eye interprets, or the brain interprets, as where the actual image is located. So here are the rays of light. If I follow them back behind the mirror, it seems like they're all coming from one point, and that's my image location. So our brain does not realize that light can be reflected off of a surface, or it can come from different directions, and so our brain will always interpret those rays of light as originating from some point, and in this case that point is behind the mirror. This is a virtual image because the rays of light don't actually converge together, they diverge, and in order to see the image we have to follow the rays of light back and see where they seem like they would be coming from. So they seem to be originating from back here, and that's my image location. And here's another picture with my object and my image, sort of another sort of description of that. So I mentioned virtual images, and plane mirrors always form virtual images. The rays of light don't actually pass through a particular point, they diverge from one another. And in order to see where the image is located, we have to follow those rays of light back, and that's what the dotted lines were, to see where it seems like the light was coming from. Virtual images cannot be placed on screens because they're actually always formed behind the mirror. The other type of images that can be formed by other types of mirrors other than flat mirrors are real images, and in those cases the rays of light actually reflect off of the surface and then they can converge together at a point. And when they converge together, that's where the image is actually formed. So real images can be formed on screens. Real images are formed on the same side of the mirror, that's the reflective side, and also where the object is located. Virtual images are always formed behind the mirror on the side that's not reflective and also not where the object is located. So when we look at images that are formed by plane mirrors, the image is always formed behind the mirror. So here's my image and here's my object, and as I move it around, the image location moves. It's always a virtual image, so the image is always formed behind the mirror. The rays of light reflect off the object, come from the object, reflect off the mirror, reach the eye, and the eye has to interpret that by following the rays of light back and see where they seem to originate from, and that's my image. The image is always located the same distance behind the mirror as the object is in front. So as the object gets closer, the image gets closer, and those distances are always the same as measured relative to the mirror. The size of the object is also the same as the image. Now this picture doesn't actually show that, but the previous picture with the candle did show that. So if this were a larger object, the image would be exactly the same size. The other thing that's true is that the image is a front-back reversal, not a left-right. So we'll see that on the next slide. So a flat mirror actually produces an apparent left-right reversal. So what does that mean? That means that in this particular picture, there's a right hand. And when you look into the mirror, it appears as if you're seeing a left hand. But that's not actually what's going on. It's not a left-right reversal. It's actually a front-back reversal. So as I look at this picture, I can see the back of the hand. But in the mirror, I can see the front of the hand. And that's what it means by the front-back reversal. So in terms of rays of light, I cannot see the front of the hand physically. I can see it in the mirror, but I can't see it physically because the rays of light that strike the front of the hand actually reflect off. They don't bend around so that I can see it on my eye. On the other hand, the back of the hand I can actually see because rays of light come in, they strike the hand, and then they reflect off and they reach my eye. Any rays of light that were coming in and hitting the front of the hand reflect off and then hit the mirror, and then when they reflect off the mirror, then they can reach my eye. So, again, rays of light are going to travel in a straight line until they hit a surface and then they can reflect off, but then they also still travel in a straight line. So it's front back. I can see the back of the hand here, but in the mirror I can see the front of the hand. The last thing that's often a question is, what size full-length mirror do you actually need in order to see your full body? And does it matter where you place the mirror? So if I wanted to see, so this is kind of a weird picture and it's an exaggerated picture, but I have a person in a top hat, really tall hat. This is their eye and then their feet. So if I want to be able to see the full image, I need to be able to see my feet and I need to be able to see the top of the hat. So light has to reflect off of the feet, hit the mirror, law of reflection has to be valid, and then it has to reach the eye. So if the two angles, the angle of incidence and the angle of reflection are going to be equal, then that would have to be like the midway point, right, between the feet and the eyes. And then same thing is true here. My arrows are a little bit reversed here, but the light would have to leave the top of the hat, come in, and then reach the eye, and that would be, would have to hit at the halfway point between the eyes and the top of the hat in order for the law of reflection to be valid. And so the size of the mirror that I would need would be right here. I need to be able to have light from the feet reach the mirror and light from the top of the hat reach the mirror and reach the eyes. So I don't need anything up above that distance or below that distance. So this mirror height is exactly half the height of the person. because I need half of the distance between the eyes and the feet, and then half of the distance between the eyes and the top of the hat, and that makes up my mirror distance. So it doesn't matter where I put this mirror horizontally, so I could move, the person could step back, step back, step back, and that mirror length would actually still be the same size, still be half the person's height. I didn't say anything about where the person was located relative to the mirror horizontally. Vertically, it does matter, because if I move this mirror up and I shift it up, then I would not be able to see the feet, right? Because I have to have some of the mirror located here in order to see the feet. So if I go further up, I won't be able to see the feet. And if I moved it down, I would not be able to see the top of the hat. So where the mirror is vertically is important. And here's a better picture other than my little stick person here. But so there's the feet hitting the eye and then the top of the head, and there's that distance that's half of the height of the person.